by the defined automata, right? So you have to identify, you have to state that for that particular automata, for the particular language, the defined automata does not exist. Then you have to go for some high level automata. Okay. So now we will go for the first level of automata. So what you can call, we'll start with the finite automata. How to define a finite automata? Anybody?
Sir, from one state it goes to another state with an input.
Yeah, that is the way defined. But how to define a finite automata? Okay, so let us do this one. So finite automata, as you see, okay, so this is, let us say, this is some kind of this is the input tab, right? So in here, whatever your strings are there, that can be there. So it is sometimes, let us say, 1 second. So let us say it is reading now 1. Now this is our control unit, right? And when it reads the entire string, it only outputs. Now the string is what? What is the string? It's a sequence of symbols, right? And again, when you are talking about a string for a particular language, right? So it tells whether the control unit, in a finite automata, the control unit, it states whether the particular string will be accepted or not, right? So this is what is the, what you can call as a finite automata. So what is the major difference between this finite automata? Why I am calling it the most simplest one? Why I am calling it the most simplest one? Any answer? Generally, you see, when you're talking about this finite automata, so you see in this finite, in this automata, you do not require a memory, right? So this automata is designed for the particular languages which doesn't require any storage, or for all those automations which doesn't require any kind of storage, right? So regular languages fall into that category, right? So now we are going to start again defining how what is this regular language. So I will straight jump into the notes. Okay, so this one was this one. Okay, so now we have to define what is how to define a finite automata. So for automatas are defined in a three ways: state transition diagram, state transition table, and using tuple notation, transition function. Right, that is how can you define the automata. Right, state transition diagrams are what they are. What you can call vertices and edges. Right. So there is a vertices are generally known as a state. Right, and the edges are what you can call as the transition that happens from one state to other. Now what is the initial state? Initial states is a special state where this what you can call this circular with q naught, this vertex will have a starting symbol in it with no prior state. That is what you can call the initial state. Final states will have two concentric circles. So this is so if a given input is there, so if the input is totally red and in the final state is this one, and we see that after transition it has reached the this one, that is two concentric circles, we can easily say that we have reached the final state. In that case, the language is accepted. Now, except final states, remaining states are non-final states where a string input is rejected, and then there are what you can call. So this is the one what you can call. This is one particular, uh, let us say, finite automata, which recognizes what? Tell me, which recognizes what? Tell me. It recognizes all languages which ends with A. It recognizes all the strings which ends with A. Now then there is a state transition table. State transition table in the what you can call left corner. You write all the states in here, Q naught, Q1. Q naught is always initiated by this one, this arrow symbol. Q1 is always what you can do. A star symbol is also there, or you can Q1 you can draw a circular over it. So that also becomes what you can call the final state. And for each state, where does it go? A, it can go to Q1. For B, it goes to Q0. It has to be defined. Now again, finite automata are what you can call. There are two types of finite automatas. One is called the deterministic, and then there is a what you can call the non-deterministic finite automata. So exactly one transition from each state for every input symbol. Now for non-deterministic finite automata, what is that? 0, 1 or more than one transition from each for each input symbol, right? Sometimes it can be null also, right? Sometimes it can be null also, right? For no symbols actually. Now, what is this one? How to understand which one is a DFA or a non-DFA? See, for A it is going to two states, right? So this is a non-deterministic finite automata. So again, it is you see in this state, for each state it is going to one single state only, right? For each input symbol, it is going from one state to another state only, a single state. So it is both a DFA and both an NFA. So we can say that DFA is in the subset of an NFA, right? That we can say. And again, in here we see that for Q1 it is jumping to Q naught on getting two symbols, that is A and B. So this is what you can call a non-deterministic finite automata. Now, what is the definition of a finite DFA? So it's a five tuple system. Q is the finite state of states. Alphabet is the finite alphabet set of symbols. Now, del naught is the transition functions. Now, in here you see Q into alphabet, it jumps to another Q, output state. So, input state on a particular, what you can call a particular input symbol. From the alphabet, it jumps to another state, Q. Right, both falls into the same states. Q naught is the initial state and F is the final state. So, how many states are there? Q, alphabet as sigma, del, Q naught and F. So these are what you can call the five tuple system, right? So again, how do you determine, how will you define another automata using transition function? So this is the way. So del Q naught and A, it go to Q1, del on Q naught on B, it goes to Q naught, del on Q1 on A, it goes to Q naught, del on Q1 on B, it goes to Q1, right? So now again, what you can call, so if I am starting with again defining the, what you can say, let us say on language, right? And we have to design a DFA. So this falls into the first kind of questions, right? So given a language, you have to develop an automata, right? Now this will follow on all the kind of languages, right? So for this one, it will fall for regular languages also, for context-free languages also, context-sensitive languages also, and you have to context-sensitive languages. You do not have to study LBA. Then we can go for Turing machines, right? So these three will be studying. So now, when you say an empty language, L is equal to that doesn't contain any string, then how what is called? It remains in the input state only, right? Now, when you're talking about a empty string, that means the language contains, it can accept, it goes to final state, accepting the empty string, then we can say directly it goes to the final state. Now, language that accepts only a, where alphabet is or sigma is equal to a, then q naught on a goes to q1a. But again, you see it only accepts a, so it cannot accept more than one a. So in that case, if it gets more than one a, it goes to q2, and then again it goes in loop in here, right? Now in here we have to understand this state. From dead state we cannot reach to the final state. Now once you have reached the dead state, right? How to define a dead state? In here q2 is the dead state. Now the from dead state we cannot reach to the final state, and again it will self loop in the dead state over all symbols defined in the alphabet sigma, right? Now, language that contains any number of s, right? Any number of means zero is also. So L is equal to this one lambda. Lambda is the empty symbol a. So in this case, this is our DFA. Are you understanding, everyone? You have to tell me when you are not understanding.
Yes.
Everyone understood, right?
Sir, if that is the DFA, we cannot see any transitions for the B.
Which one? Which question? Tell me.
Sir, that example, number 4,
Yeah, but the language you see, it is defined for only A, right? The input sigma is
but
only for A.
DFA must also have the transition for the B, right?
No, it doesn't matter like that. You see, the sigma, say supposedly I am defining the symbol, insert. So I am defining the set as let us say it the A, right? So the language that is formed from this one is which one? That any number of A's depending upon this symbol. Then what are the this one? Any number of A's means. So any number of layers. Now what is the language I am defining? Any number of A's, right? Right. Now in here you see that the input symbol, sorry, the alphabet does not contain B, right? So there cannot be any B in there. So it can be lambda, right? Then again A, it can be double A, it can be triple A, and then I can say dot 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 any number of A's, infinite number of A's, right? But it doesn't contain any B. It understood?
Yes, sir.
Now if I put it in here B, and again I says any number of A's, then also it will not contain, the language will not contain anything or contain B. But if I say the complement of this language, then it may consist in a single number of B, right? But in this particular alphabet, we only consider there is only one symbol, that is A. Okay, is it understood?
Yes, sir.
Okay. Okay, now let us develop this one, right? So this is Q naught. Q naught is our initial. And okay, and when I say it is concentrated, when I'm saying, 1 second, any number of a's and it contains lambda also, that means it can reach to a final state using, it can reach to a final state using empty symbol also. So this is also what you can say. 1 second. Okay. So this is itself a final state. The initial state is also is a also a final state. 1 second. Okay, it reaches a final state. Then again, when you are saying that any number of a's, so let us say develop for this a, right? So we'll just copy paste this one. So I'll just write q1, or I write qf, right? Qf is final. So again, so this is our qf, and it reached here. Okay, right? It is a q0 for a also, it can reach qf, right? But again the question is that should I create another a, should I create another state? Now let us understand. So this is, now should I create double a for this a also, should I create? Is this, but this is right, I can create, I can say write qf1. But this is what you can say, we should not do like this. Then again for triple a we should create another final state. No, we should not go in this fashion, right? So we have to also think of creating a, what you can call an optimized automata. So I'll just delete it, right? Right. Instead of for double a, what we do, we just put a this loop symbol over here. Okay. And then we put this thing in here. So for any number of a's, now it goes in this one. So for two states, I can develop this. Right. Understood this one? Okay. Is this point understood, how to create a DFA from a regular language?
Yes, sir.
Okay, so let us go into this one. So language that contains any number of a's. So this is also okay, right? So you can do like this also. Over the input symbol also you can do it, right? And okay, so 5 is also same. N is greater than equal to 1. So in this one, that empty symbol is not accepted, right? So in this case, we cannot make the Q naught as the final state. Okay, today I will stop it. So I'll give you some homeworks. Okay, is it okay if I give you some homework?
Sure, sir.
Okay. So today we'll start. Today we'll stop in here. I'll give you some homework. You just do those homework and update me. Okay. I'll create a Google Classroom for you. Give me some time. Today is a little bit night time. So by I think 10 or 10:30, I'll be giving you that homework. You just submit it tomorrow there. But you have understood today's class, right? Hello.
Yes, sir.
Okay.
Yes, sir.
Okay. I think I have recorded the session. Your attendance is with me. Okay. So I'll stop the recording session.